Hey, what's going on, everyone? It's Grayson here from Based Theory. I know it's been a minute. I've been on a long trip, but I am very happy to be back with you all. I will begin putting out videos again more regularly. Sorry for everyone. Thanks for being patient with me on this. So I'm just going to open up the stream right now. Just let people join in as they please. We're going to be mainly talking about the results from the James Webb Space Telescope. Most people are familiar with it. It's like one of the most expensive scientific projects in recent decades, and a lot of misinformation has been spewed about, particularly by creationists, but by a lot of people online. Misinformation about what these results from this James Webb actually are. So to kick things off, I'm going to add Andrew to the stream. He came on. Hey, Andrew, how's it going?
Good. Thanks for having me on. How are you doing?
I'm doing well. I've seen you on a few of these creationist videos about the James Webb, particularly the one that
Yeah.
Sal and Rebecca put out a little while ago, whom I did have a debate on the topic of the Big Bang with. So you are familiar with just how people have been
How far it's
misconstruing
gotten.
Webb
Yeah.
results.
Yep.
Yeah.
Yeah.
So I just wanted to, as a brief introduction, I mean, James Webb is a pretty big deal. It was about, I think, somewhere around a price tag of 10 billion, which is significantly more than the Large Hadron Collider, which is pretty much the most complicated machine that humans have ever designed and one of the biggest scientific projects of the 21st century. So the James Webb is significantly more expensive, significantly, is a little bit of a bigger endeavor in a lot of ways. So this has been pretty huge for, science and what we're going to be discovering. So I think maybe we'll save some of the speculations about some of the things that the James Webb might discover, or in its 20-year lifespan, towards maybe the end of the video, because I wanted to get into some of what people have been misinterpreting from the James Webb, specifically in regard to the most distant galaxies, because the James Webb is not just for looking at the early galaxy formation. It's also about exoplanets, even just looking with new eyes in our own solar system, measuring some of the molecular composition underneath of Europa's ice sheets. I mean, there's a huge number of applications for James Webb, and the amount of data that it's going to be providing over the next 20 years is going to be pretty significant to our understanding of a lot of science. So I wanted to start with here we go. We got a question in the chat already from Taylor K. She says, how many exoplanets have we discovered so far? I think as of last month, that number is around 5,500 verified exoplanets. So we're kind of still in the adolescence or the infancy of exoplanet research. The very first exoplanet, I believe, was discovered just in 1995. So it's only been my lifetime. I mean, that's the year that I was born.
Right.
So it's still a pretty relatively newly burgeoning field. So look
But
at
it
this.
is
We
part of
have
the amazing thing about it too is that even though we've kind of just in quotes started off from the 1990s, we've already discovered, like you said, 4 or 5,000 last I checked. So
yeah.
that's
So
still
this is already
pretty
more people are
significant.
joining this stream than I anticipated. I thought we would have time to go through a little bit of the James Webb results before people started piling in, but we have my old good friend here, C Science, joining the stream. So C Science, been a minute. I'm letting you in. I'm letting you say your piece, but just try not to talk over people. That's the only thing I ask. Are you there?
Hey, thanks, Grayson. It's good to see you. Yeah. Can you hear me? Am I coming through? All right. How you doing,
but I
buddy?
think that you might be echoing.
Yeah,
just
but I
a
think
little
that
bit.
you might be echoing
Yeah,
just a little
you're
bit.
echoing.
Yeah, a
Well,
little bit.
I
A little bit.
probably can't help that, man. But it's good to see you, man.
Okay, well, the echoing thing kind of is a little bit annoying for viewing. So if you can't sort out the echoing issue, maybe get some headphones or something. I don't know, but at least I guess leave yourself on mute unless there's something that you really want to say. Then. Okay, cool. I think we're gonna just so specifically, I wanted to show people what these most distant galaxies that have been seen in the James Webb look like, because especially when they first came out, a lot of the redshift values were so extreme that you had science journalists labeling these impossible galaxies. They were saying these were impossibly far away, impossibly bright. The word impossible was thrown around a lot in the initial weeks of the press. And what has happened since then, again, it's been 1 year since James Webb has been operating. What has happened since then is that the machine was recalibrated, which brought a lot of those redshift values down. And then we additionally got the actual spectra for the galaxies, which rather than just looking at the raw photometric redshift, when you get the spectra, you can pinpoint that Z value, which is a measure of redshift, much, much more precisely. And what happened is a bunch of those really insanely far galaxies, Z scores of 16 or whatever, were all brought down to within, a sane and sensible range that was fully expected, under a Z value of 14, which was about what the expectation was. And we still have a lot more very distant galaxies to be seen. But I just want people to actually get a visual of what these are looking like, because the number one biggest misinformation that I see people saying about these James Webb results is that these most distant galaxies look just like modern mature galaxies that we see nearby today. I've seen lots of people saying that they're just elliptical galaxies like we would see today. So I'm going to try and share my
just like the Milky Way or whatnot.
Yeah, exactly. So like I'm going to go. Okay, so can everyone see that? So those are the 6 that are the very furthest redshifted. You can see that, Andrew?
Yep.
Yeah, so these are the 6 very furthest redshifted galaxies discovered by James Webb so far. As you can see, they look like a bunch of fuzzy splotches. I mean, you're not seeing anything. I mean, this is the very farthest one here in this corner right here. And you can see, I mean, that's what we're looking at. And for all the people like James Lyle and a lot like Rebecca, all these people saying that this is a modern, mature looking like spiral galaxy. I mean, this is. I hope that you can see, like, it's a little bit ridiculous to be saying that these look like exactly like modern, mature galaxies. I mean, most of these are hardly recognizable as anything more than just some sort of weird globular cluster.
It kind of just comes to show the sheer distance of these objects is insanely powerful. A telescope as the James Webb is, they still come out as these fuzzy, sometimes irregular objects.
Yes, and I also want to make the point. So these are only the 6 that are the farthest that we observe. So I wanted to make the point that as well as when we broadened it to just looking at the galaxies that we observe at the highest redshift, not like the most extreme, but just like within about the first 1 billion years or so after inflation, then when we broaden that, we actually begin to see something that is very different than what we would describe as modern galaxies. So here I have a page from NASA here to talking about some of this, and here you can see directly from NASA showing that these ones found by the Eiger group. Again, we see none of them really look like stereotypical shapes of galaxies that we would see nearby around us, modern galaxies. And you can even see in the description here that these include never before seen structures. These distant galaxies are clumpy, often elongated, and actively forming stars. So this is to contrast them with more modern, more mature galaxies that we would see near us. Again, people like James Lyle and Rebecca and Sal are trying to make the claim that these galaxies that we see very distantly are just the same as modern galaxies. And again, we're going to get through more details on that with stuff like their metallicity. But just from what we can see visually, these don't look like modern galaxies. We cannot neatly box these into spiral galaxies, elliptical galaxies. Like we cannot neatly put these into modern categories. Andrew, any thoughts on this so far?
Yeah, I guess two things. So, kind of just to add on to what you said there, they're also significantly smaller than modern galaxies in a sense of like a Milky Way or Andromeda type galaxy, that sort of thing. But the other thing was I like how you mentioned the star formation rates, and I feel like that should be talked about more because when you think of what a galaxy is, it is a collection of stars. Like the formation and death of stars is kind of the life essence of that galaxy in that sense. And so the fact that these very distant high redshift galaxies are forming stars at significantly higher rates than today's galaxies, that should be significant as well.
And Taylor K did have another question about specifically the exoplanets and whether or not any of the ones that we're finding are in the Goldilocks zone. To my knowledge, I don't know the exact number, but to my knowledge, there are several exoplanets within the Goldilocks zone. But so far, we still have not found any exoplanets that you would describe as being like habitable, as in, having a breathable atmosphere or being suitable for life as we know it. So that's still a bit farther away, but we have found exoplanets within the Goldilocks zones.
Also by James Lyle. Did you mean Jason Lyle?
Sorry, yes, Jason Lyle. Thank you for clarifying that, because I was actually about to bring him up again because for people that don't know, he is an actual astrophysicist, creationist, and he'll make comments about well, we know that not all the heavy elements came from stars and supernova because oxygen was here on Earth on the first day of creation, and the stars weren't created until the third day. So this is the kind of I mean, he will supersede his knowledge of astrophysics with his knowledge of.
I've actually never heard that one before, but it's kind of amusing.
Yeah, so that is what he will claim. And we're going to go into some more of Jason Lyle's claims here, specifically because he's the one who claims that he has predicted what the James Webb telescope is going to see, and he says that the results are in line with his predictions. So this is what we're going to be debunking today, because he says that the galaxies that we're seeing with the James Webb, the very earliest galaxies, he says are modern, mature galaxies. And this is patently in contradiction with the actual observation and evidence. So, C-Science, I see that you're back. Were you able to fix that echo?
I don't know. Let's see.
Okay, well,
how's it coming?
As long as you don't have yourself muted, then we should be able to hear if we're echoing. So far, I don't hear anything. So it sounds successful.
Yeah, I don't hear anything.
Sweet.
Oh, that's excellent. Well, how you doing, buddy? I just wanted to chime in and say hi to you and make a couple points when you're ready. So good to see you.
All right, cool. Let's just get through this first point about why these James Webb objects that we're seeing at like the most redshifted are qualitatively and quantitatively different than modern galaxies. So I'm just going to make one more point on that topic, and then we can get on to discussing it. And then I also want to bring up the point that so far the James Webb data is actually validating the predictions of the Big Bang, specifically in regard to reionization. So that's pretty exciting about, it's basically the opposite of most of the creationist claims and Eric Lerner types with plasma, whatever.
Yeah.
Saying that the James Webb has somehow debunked the Big Bang. It has done the exact opposite and validated its predictions. So we will get there. And we will also potentially discuss this new paper by R. Gupta from last month about how the universe might be 26 billion years old. And no, that is not very likely. I am not very impressed with Gupta's work on his paper. So
strictly, yeah. I'll have stuff to say about that later. Sorry.
Okay, so I'm going to share one more screen here, which is, like I said, so Jason Lyle's prediction was that what we should see when we look at the spectra for these very most distant galaxies is that we should expect to see galaxies that look like the galaxies that we have today in terms of their composition. And so I wanted to show, let's see, I think, is this the paper? No, sorry. I'm just trying to pull up the actual paper that I had. Hold on one second. I wanted to show the actual data on the metallicity. Here we go.
And
The
these are, just to clarify, for spectroscopically confirmed galaxies so far.
Yes, for spectroscopically confirmed galaxies. There are a very small amount of galaxies in the James Webb that have so far been validated with spectroscopy. Right. But there are a few, and this is one of the early papers. I'm not sure if this paper has been through peer review yet, but this is actually on the James Webb Telescope's official website. But it doesn't look like it's been through any journal or anything yet. But this is the spectroscopy of 4 metal poor galaxies beyond redshift of 10. So those are the very farthest distance galaxies. In fact, I think the farthest known galaxy to date is one of the ones in this study, which is that galaxy is known as JADES GS-Z13O. And that galaxy, so and that galaxy is the very farthest galaxy that we have been able to see. And look at that, it is extremely metal poor. So just from this study here, and this study, anyone can go and read it and look at the actual data themselves. When we actually look at the metal composition, so the composition, they call it metallicity. It's not just metal. Stuff like oxygen, stuff like carbon is all counted here. The metallicity just means heavier elements, like elements that are heavier than just hydrogen, helium, and lithium, and the things that would have been created in the Big Bang. So we can see here that as a percentage, these heavier elements are very low, much lower.
Are you trying to show a graph right now?
Huh?
I'm only seeing the title. I don't know if that's just
no. This is fine. I just wanted to cite the paper itself. In the title, you can see there are 4 metal poor galaxies beyond the redshift of 10.
Okay.
If we scroll through, I mean,
sorry, I was just making sure in case you were trying to present something else.
No, I didn't recall much. I mean, you can have some of the data here that shows some of the metallicity, but I didn't find like any, I mean, there are graphs, but they're not easily deciphered by lay people. The point was mostly, and I just wanted to show this paper just so that people could look this up themselves and read it if they were curious. The point is that these most distant galaxies that we observe are extremely metal poor, much more metal poor than our sun is. Even the most metal dense ones that we observe are still less metal dense than our sun. So it's not like we're just finding modern galaxies at these very high distance redshifts. They're fundamentally different shapes and have much lower metallicity, which is what we would predict with the Big Bang lambda CDM model. Let's see. It looks like.
Now, I have heard some criticisms that from some people that we should be finding population-free stars, but in my mind, at least to my understanding, we shouldn't be seeing that in at least these types of galaxies, because whenever those stars were around, they'd be very massive, of course, and so they'd have very short lifetimes. And at least for these galaxies that are 300 to 400, 500 million years after the Big Bang, at least I wouldn't expect many of those stars to be left over. But
yeah, and that's a good point. But it is somewhat expected that if anything was going to see these population 3 stars, and just to clarify that for those watching, a population 3 star is a theorized star, which would be like a first generation star, the very first generation of stars formed after the Big Bang. So these should have basically no metallicity. This would be the very first generation. So the earliest distant objects that we're seeing so far in James Webb, these are not the very first generation of stars. These are not population 3 stars. But if there was ever a scientific project that was going to see Project 3 stars, that would be the James Webb. It's a
Right.
much more rare observation for the reasons that Andrew pointed out, but it is theoretically possible to observe if we get just the right kind of Einstein ring gravitational lensing effects. We could hypothetically be able to see a population 3 star, and this is a prediction of the Big Bang model and would be one of the most exciting discoveries for the James Webb to make. So I'm still personally hopeful. I know that some of the scientists that work on the James Webb have hinted that we may be getting some papers with possible
We're
population
getting closer.
Huh?
I said we're definitely getting closer.
Yes, and I just want to
probably
add
on the very-
Dave from Captain Desk to the stream. Hey, Dave.
Hey, Dave.
Hello, everybody.
Yeah, and also Mr. Colby said, "Oh, USA Today said 26 billion." So I'm sorry, Mr. Colby, but USA Today, not a scientific source. Those are journalists trying to get clickbait titles. There's only one scientist that he has even proposed this figure, and that is R. Gupta in his new paper last month, which we can go into, but is not. Let's just say that the paper has not been accepted by the scientific community, and not a whole lot of people are impressed with it. We can get up to that. Yes, see Sydney Raptor here saying cosmologists are very skeptical of Gupta's speculations. His population did not take into account. Yeah, there you go. So there are reasons to doubt his model. He's basically, all he's done is combine the lambda CDM model, the traditional story of the Big Bang, with a tired light model, just to push the date farther back. It creates more problems than it solves. I mean, tired light is pretty debunked at this point within mainstream science because we don't see any blurring effects. Sorry, no blurring, no tired light. So
on a kind of more charitable end, I think it isn't like pseudoscientific work like we see from Eric Lerner, for example, or stuff like that. I think the problem is that people are construing it as beyond what it was kind of designed to do at this point, which is provide a what if scenario. Like, okay, what if some of our assumptions here are to be modified to some extent, and now people are taking that and saying, oh, well, the universe must be 26.7 billion years old, and that's not what it was trying to do.
So I'd really, really quickly like to address two comments by Tanya Brown in the live chat. The first one, this is going to blow your mind, Tanya. So she says that nobody has ever seen a star being formed. Oh, I see. So, Tanya, this is going to blow your mind. I'm about to show you a picture taken by the James Webb Telescope of a star being formed. Are you ready? Because this is exactly what you said that no one has seen. I'm about to show you the picture, okay? So here's from NASA's website itself, okay? Here's a picture that the James Webb took of a star being formed. So in the middle here, this is a protostar. You can literally see the gases coming in. These dark patches are not emptiness. These are just not illuminated by the protostar. And you can see here that there's an accretion disk, exactly as was hypothesized to be how our solar system formed, with a mass of molecular dust coming together, forming an accretion disk and a protostar. Here's a literal picture of it. And you can see this on NASA's website. The Webb telescope catches a fiery hourglass as new star forms. So there you go. I hope that you will no longer repeat the misinformation that Kent Hovind likes to peddle that says nobody has seen a protostar form. We saw the first one in 2004. So it's been almost 20 years that we have seen stars forming. So I hope that you will no longer repeat this lie. And their second comment here that says, I also think that secular scientists are being disingenuous to say their expectations were met. It may not be as bad as first thought, but the observations don't match their predictions. All right. So this is a little bit more of a valid point because there were certainly some surprises with the James Webb results. However, what we see here is, I want to share this paper because what I think Tanya is missing here is that the predictions, right, were not based on the lambda CDM model. The predictions were based on simulations of galaxy formation, right? That's how we formed our predictions for what we should observe in the James Webb Telescope. Because again, it's not looking all the way back to, like, you know, recombination or anything before then. It's looking at the first billion years. It's not looking at the Big Bang. It's looking at that first billion years or so. And so those predictions were just from our computer simulations based on very limited data. I mean, if you had talked to the scientists, they were not saying with any amount of confidence that these simulations are representative of how they actually formed. They're just our best guess based on the data at the time. And wouldn't you know it, here we go. I'm going to share another paper here from 2023. No tension. JWST galaxies at greater redshifts than Z over 10 are consistent with cosmological simulations. So this right here, they got the most powerful simulation that has ever been run, Renaissance. And this is only taking advantage of like our very most modern computer simulation technologies, found that they are in agreement with the JADES, which is the James Webb and Sears. These are all James Webb galactic surveys. So we find no tension between the Lambda CDM model, which is our current cosmological model, such as Big Bang. So there's no tension between the Lambda CDM model and current JWST measurements. Again, this paper is from April 2023. This year, they ran new measurements with way more computer power than ever before and found that there was absolutely no tension. Okay, these are not impossible galaxies. These are not in contrast with our predictions or our models. I mean, this is all just a bunch of misinformation peddled by people that already presupposed that the Big Bang did not happen by the way that science says. So,
like you said, it's interesting that these galaxies that have been spectroscopically confirmed had their spectroscopic redshifts taken rather than just images. They're turning out to be actually consistent with the Lambda CDM model.
Yep, exactly. So everyone's saying, that these are impossible galaxies, that they're in total conflict with the Lambda CDM. I mean, this is all just a bunch of hot air. The really hilarious thing is that the James Webb was only designed to see, in the infrared spectrum. So people that are saying, oh, it's seeing galaxies that are farther away than the Big Bang would even allow, that on its face of it is ridiculous. Because if they were more redshifted, then they would no longer be in the infrared. They would be in the microwave spectrum, which the James Webb is not even designed to see. So it's physically impossible for the James Webb to be seeing anything that's more redshifted than the cosmic microwave background, because it literally doesn't have the sensors to be looking in the microwave spectrum. So it's just on the face.
I think where the claim comes from is like them suggesting that certain star populations in those galaxies they look as if they're a billion years old, but I've never really found out where those estimates came from other than like blog posts and whatnot. And I'm not exactly sure how you'd estimate that anyway with the limited data that we have right now, like you were saying.
So now Tanya has come back and said, show me a picture in 100,000 years, and if it's a star, I'll concede you're right. Wow, very, very honest and good faith of you, Tanya, to just show me, come back in 100,000 years and show me again. All right, so basically your position is unfalsifiable. Good to know. Taylor said that the star forming was a pretty picture. I agree, Taylor. Tired light is just the debunked notion that light loses energy as it travels great distances. So this has been debunked by observation. So yeah, now to the fun part, right? We showed how all this misinformation that skeptics and detractors have been piling forth, like primarily spewing from Eric Lerner, but also a lot of these creationists like Jason Lyle, is in conflict with the actual results that we see from the James Webb. These are very clearly not modern, contemporary, mature galaxies, just based on the actual data from the James Webb that we know that that's patently not the case. So now I made the claim earlier. I said that the James Webb data is actually validating the predictions of the Big Bang, quite to the opposite of what all these headlines that you see. So this is what I find is really interesting here. And this is from NASA's website. So I want to show this again here. So on NASA's website, we can see here, and this is what we were looking at earlier with the galaxies, but on the same page, where you can see this article, everyone can go look at it. It's from June of 2023, so just last month. And here we have this nice graphic right here. So this is referring to the age of reionization. So after you have recombination, which is the event that forms the first atoms from a universe of plasma and created the cosmic microwave background that we observe today and is one of the strongest lines of evidence for the Big Bang. After that period, you basically have a universe composed of molecular gases, like hydrogen and helium gases. So you go from a period that had pretty much entirely plasma, which is ionized gases, or matter, ionized matter. And you go to a period where you have essentially no ionization. You just have these molecular gas clouds. So as stars begin to form, the stars are going to output a bunch of energy and radiation, and this is going to be coming into contact with these molecular gas clouds, and it's going to knock off their electrons. It's going to re-ionize those gas clouds. So that's what's being illustrated here in this. This is sort of a theoretical construction here of what the theory would say. So see, the very first stars form and galaxies assemble. So these would be those population 3 stars that we would be talking about, the very first generation of stars. And you can see that they're forming these little bubbles. So these bubbles right here are changing the gases around them. They are reionizing all the gases around them to form these kind of transparent bubbles around these stars. So you see these areas of the transformed gas expand, and eventually you end the period of reionization by having the clear universe that we observe today. Hopefully this is making sense to people just on a theoretical basis of this is what would be predicted by the lambda CDM, the Big Bang model. You would predict that you would have this observable period of reionization where we should be able to detect these bubbles, these transparent bubbles of reionized gases surrounding the very earliest galaxies. And what do you know? But that's exactly what has been found by the James Webb. Let me present another screen here with the paper. So here we go. A large sample of galaxies between these Z values of redshift and direct evidence for local reionization by galaxies. So this is part of the EIGER team, this EIGER. This is a series. I think they've done 3 papers on this subject. It's pretty awesome work that they're putting forth. But we are literally seeing the reionization happening, these transparent bubbles around the very earliest galaxies. Again, we don't observe those in any contemporary galaxies, but we're seeing them in these very earliest galaxies, these very farthest distance galaxies that we're seeing. We're literally seeing the reionization happen, which is a confirming of the prediction of the Big Bang lambda CDM. So, Andrew, I don't know if you've heard of any of this reionization stuff, but pretty interesting, right?
Do you know any of the specifics of how they like detected or verified this, or?
Yeah, let me open up that NASA.
Because I'm actually interested to see how they would have measured this.
Yeah, it's fairly complex, but here they mention at the bottom here where they have where they've gone into basically there's a number of different ways where in one of them they looked at quasars, in other ones they're looking at here in the actual paper they kind of go into some detail, but it is a little bit above my head about how they're actually observing this. But basically they're looking at the light of quasars and how like a very, very bright quasar is being like the light is being modulated as it patches through these patches of more opaque non-ionized clouds versus patches of more transparent clouds, and what effect that has as the light passes through. And by looking at multiple Yeah, and looking at that basically over time, they've been able to construct like kind of three-dimensional like visuals of where these transparent bubbles would be surrounding like a halo around each of these early galactic objects.
Yeah, I'm familiar with that work. I wasn't sure if it was being applied to these more recent findings or not.
Yeah. So yeah, very interesting to me because I was sort of following the James Webb, hoping that we would see further evidence of reionization, because I believe a couple years ago there had been a radio observatory that had seen it's like some evidence for reionization. But we're seeing more and more. I mean, the evidence for the era of reionization is pretty much a direct prediction from the Big Bang model. So again, this is the more information that we're getting, the more the Big Bang is being confirmed again. So I mean, we
and
have,
like you said, it's good to cross confirm what the JWST is seeing with, like you said, these radio telescopes on the ground. And
yeah, exactly. And it looks like, I mean, C Science was saying a lot of stuff in the private chat, which I wasn't really reading. But it looks like he has left and no longer wants to offer any criticisms or anything. So I know that in previous discussions there have been some creationists that had expressed an interest in talking about the James Webb. So that's why I wanted to make this video, to see if any of them would actually be able to come forward and try to actually talk about the James Webb results and not just repeat, what Eric Lerner has said or whatever. But I guess C Science was the best that they could come up with. Let's just,
well, as a layperson, when you get a second, I got a question as a layperson. So go ahead, Andrew.
Okay, yeah, I just want to respond to Tanya Brown's comment about the newer simulations, if you can highlight that one.
Yes.
Yeah. So what they're doing differently in these newer simulations is, rather than just accounting for the effects of gravity due to dark matter, which obviously doesn't interact with electromagnetic radiation like light and other stuff, so it doesn't really interact with anything else than via gravity. That's a lot easier to model than, say, all the complex gas dynamics between all the clouds forming in a galaxy, clumping together, that sort of thing, all the supernovae going off, all the for example, the supermassive black hole at the center of most galaxies that can emit a lot of radiation that can then affect everything else going on in that galaxy. So it's a lot of complex feedbacks in this, the baryonic, that's a technical term for this kind of matter, side of things. And that's what we're incorporating more and more into these simulations at the same time as our computers are getting more accurate and complex, obviously, more computational power.
Yeah, it's pretty wild that her initial reaction to seeing that paper with the new Renaissance simulation is to basically allege a conspiracy, where she's saying that how convenient that these new simulations, after they've made these James Webb observations, now these simulations fit their model. It's like alleging some kind of fudging of the data to try to force the model to fit the James Webb, rather than like, just, I mean, that, like, she doesn't actually know any of the details for how the Renaissance model was constructed or how it's run. She just immediately launches into, it smells pretty fishy. Sounds like they just fudged their numbers, which is, I guess the only,
I guess that's a typical misconception, I guess, about science in general, though, is that if newer data comes along and you update your model, or just incorporate data that you weren't able to previously, then that must be fudging everything together to make it work somehow.
Yeah, I mean, science is provisional. All empirical things are. So okay, and here she has said that.
By the way, I hope my audio has been coming in okay so far.
I certainly haven't had issues with it. So,
Okay.
yeah, basically saying that the
Sound
Big
okay.
Bang is unfalsifiable, that scientific observations show equal amounts of matter and antimatter produced when converting energy into matter. How does this not falsify the Big Bang? So, some sort of, uh, symmetry breaking between matter and antimatter. I mean, it's still a mystery. I don't see why that would debunk the Big Bang. I mean, yeah. I mean, Andrew, do you
I
have
mean,
any thoughts
it's
on
an
that?
open question. Yeah, it's definitely an open question in cosmology, but I would see that more as an indication that our standard model of particle physics is incomplete, rather than the Big Bang as a whole is wrong, if that makes sense. Like, clearly, like you said, there's some kind of symmetry being broken, and I know in some cases we even have evidence where those symmetries can be broken by known physics. So it's not therefore totally unreasonable to infer that maybe with some more physics that we may discover in the future that those symmetries could be broken even further to allow this asymmetry.
Yeah, and the hilarious thing about this, right, is that we still have the cosmic microwave background, which shows pretty clearly that at one point the universe was in a state of essentially 100% plasma, or a plasma and radiation. And so, like, yeah, I mean, if she's saying that somehow the difference, the symmetry breaking between matter and antimatter somehow invalidates the Big Bang, well, you're still left with the cosmic microwave background, which literally has no other physically plausible explanation other than recombination after the Big Bang. So, really quick,
Well,
Dave, I know you have a
that's why I find. Sorry, one last thing. That's why I find always convenient, or it almost seems convenient how they always go after the galaxy formation stuff rather than Big Bang nucleosynthesis or cosmic microwave background predictions, kind of the more solidly confirmed stuff. That just
yeah.
strikes me as odd.
Real quick before your question, Dave, Taylor's asking, is dark matter even real? So basically, we've seen the evidence that dark matter exists through its interactions with gravity. So if dark matter is not real, then there's something out there causing all this excess gravity in like patterns that very precisely fit to dark matter occupying that space. So, I mean, we certainly have plenty of evidence that dark matter is real. We just don't know what it's composed of.
I want to add something to that, but I'll let Dave ask his question first.
Yeah, well, I just wanted to ask I had sent Grayson an email asking about something Jason Lyle said, because I had put up a comment, kind of tongue in cheek. Are there any fields of science that creationists do not deny? And he kind of dodged answering the question, but he said, creationists do good science. I made predictions that came true about the James Webb. And Grayson answered me, and I appreciated it. But one thing I wanted to clear up was I understand that basically he rejects the Big Bang, so he expects to see everything immediately after the Big Bang as it is today, including heavy elements and everything. And one of his main predictions that I didn't understand was that he says that the James Webb proved that there were no heavy elements in genuine population tree stars. Is that correct?
Well, so far, there is not any consensus about the James Webb actually observing population 3 stars to my knowledge. So, like, theoretically, a population 3 star should have the smallest amount of heavy elements of any star observed ever. So,
just hydrogen and helium.
But that hasn't been observed.
So far, I mean, there have been some claims of possible population 3 star candidates, but so far none of them have passed like any kind of test of significance.
Very
so
circumstantial stuff.
Yeah, none of them have gone like the 5 sigma level of confidence that is pretty typical for physics. None of them have reached that level of confidence that what you're looking at is a population 3 star so far. But again, the James Webb's only been operating for 1 year. It's expected to be operating for 20 years. So over that 20 years, our chances of being able to detect something as rare as a sighting of a population 3 star will only go up. So I would, I would probably put money on us seeing a population 3 star if I had to put a bet on it. But it will be a very exciting day for science for sure if they're observed. And one other thing I should clarify, those 6 most distant galaxies that I showed at the beginning, it's not even entirely clear that those are galaxies. In fact, a paper just came out just a couple weeks ago, or maybe it was back in April, but this year for sure, that was a paper walking through how the most distant object there, that Z13O that we were talking about, that might not even be a galaxy. In fact, they were theorizing that actually could be the very first sighting of a dark star. So this kind of goes back to what Taylor was talking about with dark matter, and asking here, is it composed of atoms? No, Taylor, it would not be composed of atoms. Whatever dark matter is composed of would not interact with the electromagnetic force. So, I mean, the electromagnetic force is kind of one of the key forces that atoms interact with famously. I mean, that's why when you touch something, that's why you don't just pass through it, is because the electromagnetic force between the electron shells makes things, physically repel from each other. So you touch things instead of passing through them. So dark matter would not interact electromagnetically.
I kind of threw the term out of baryonic matter. That's kind of
yes.
For the audience,
so it would
pretty
not,
much the same thing as atomic matter.
So it would not be composed of atoms. It would not be composed of atoms, but there are hypothetical objects. Again, the paper did say that this very furthest object that the James Webb has observed could be a candidate for a dark star. And what a dark star is a star that instead of burning hydrogen and helium, as in like fusing them for energy, it actually burns dark matter. So these kinds of stars would be fueled by dark matter and are, potentially some of the very farthest things that we're seeing are not even galaxies. They could be far more exotic objects like dark stars or any number of things. So far, we don't even know enough about these most distant galaxies to definitively even say that they are galaxies. So people like Jason Lyle or Rebecca, like saying that these are just the same as what we would have expected, just the same modern mature galaxies that we'd expected, are just patently wrong based on all available data.
So they're making it up. There is no such data. Is what I'm getting.
I mean,
bottom line
should know better as well. He should know better because he has the credentials to be able to properly understand the data that the James Webb is getting, and knows that they don't have modern mature metallicity. They don't have the kinds of shapes that we observe in the galaxies nearest to us from mature galaxies to have. So yeah, I mean, it's
well, you know what they do to lay people like me. They throw things out there, and I'm like, I don't know. I got to go look. You know what I mean? And then he just gave the smug look, like, ha 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 ha. And so that was just a fib. So okay.
If I just on this point specifically, and this is like one of the most frustrating aspects for me, is that, like you said, the James Webb is expected to do all this great science over the next few years, and yet it's only been into a single year now, and the media and creationists have already jumped on every single thing that's come
they
out.
didn't even let it get to a year, Andrew. They did
Right.
in the first 2 weeks of its operation. Eric Lerner came out with that article, "The Big Bang's being disproved." I mean, totally talked out of his what.
Yeah.
And Tanya here said, "Where has the symmetry been broken?" Do you think that she's just asking for just general examples of symmetry breaking in physics? Because you said that has been observed before. I would direct her to look at CP violation if she wants an example of observed symmetry breaking in physics. But if she's talking about specifically with matter and antimatter, all you have to do is look around, Tanya. Where's all the antimatter? I mean, we know that the symmetry has been broken because everything we observe around us is made of matter, not antimatter, or the majority.
Well, yeah, that and the matter antimatter asymmetry. We know the general conditions that have to be met in order for that to have occurred. We're just at this point trying to find, okay, what explanation is there for how those conditions could have arisen. the breaking of the symmetry I was referring to were certain experiments where kind of between matter and antimatter particles, it turns out the weak nuclear force actually kind of treats them slightly differently. The question is whether that can fully explain this asymmetry, but that's kind of the point I was trying to make, is that,
Andrew, I think that you might have some noise going on there in the background. And she also talks about the cosmic microwave background. Isn't it also consistent with Lerner's model? No, it is not. Eric Lerner cannot explain the cosmic microwave background using any known physics. Is it also possible for a created universe? I mean, sure, God could just have created it that way. And that's possible for literally anything. Any observation in the universe, you can just say, well, God did it that way. That's not really a model. It's also a problem for you. It's not actually. How is it the same at both ends of the universe? So this is just a misconception of what the cosmic microwave background even is. I mean, if you understand what the cosmic microwave background is, then you would understand why that question is a little bit nonsensical, because if it necessarily is the same in a 360-degree sphere around us everywhere we look, that is a necessity based on what it was and how it was created, right? If the universe 380,000 years after the Big Bang was full of a plasma, and then it cooled down and got big enough to the point where that plasma could combine into atoms, the release of the radiation would be able to traverse freely, so that it's no longer absorbed by all of these ionized plasma particles, and it would be able to travel freely for the first time in the universe at that point. So if the universe has continued to expand since then we would expect for that initial light that was created there to be extremely redshifted all the way to the microwave spectrum, and to be coming from every single direction when we look around. And that is exactly what the cosmic microwave background is.
Hey, gentlemen, I got to go get something to eat, but I wanted to say I appreciate both of you. Whenever I'm picking your brains, you guys always answer me in a way that I can understand, and us lay people appreciate it.
Hey, well, thanks for stopping by, Dave.
It's always good talking to you guys, and I say thanks for clarifying that. And
yeah, no problem.
Well, Jason Lyle definitely needs somebody to challenge the things that he says. So if he's open to a debate, I would definitely love to debate Jason Lyle.
I'm going to answer his little comment in a quickie review video as soon as I get a chance.
Well, yeah, everybody check that out. Look out for that, Captive Desk.
I just want to tell you, Andrew, I just recorded my first creationist science clips with turning the cards and turning sand timers, like I was telling you about. Okay. So I'm editing. I'm editing. Maybe tonight, maybe tomorrow. If I get it done here tonight, it'll be.
No need to rush.
First one is underway, and then we're gonna do the rest, the flood and everything else. So that's what's coming. So, but I wanted you to know it's underway, sir. It's underway.
Yep.
and I wore my Hawaiian shirt.
Cool. All right. Well, thanks, Dave. Thanks for stopping by.
All right, guys. Have a good night.
Cool. And yeah, I mean, if anybody thinks that Eric Lerner actually has an explanation for how the cosmic microwave background is created, I mean, maybe read a bit more into it and see what kind of ridiculous physics he's trying to make up to explain this. Andrew.
I mean, I would. Are you gonna say something?
No, you can comment.
Yeah, I was just gonna say, for anyone curious about how well Lerner's model matches, or should I say doesn't match, the CMB spectrum, I think it was like the predictions he was making once the Kobe satellite came out in the early 1990s, like even that alone showed that his model didn't really match the data. I direct anyone who's curious about that to look up Ned Wright's good article, I guess, on errors in why the Big Bang never happened by Eric Lerner, or something to that effect. But
Okay.
he goes a lot into the specific details of a learner's model doesn't match the CMB, and even if it did match the CMB, it doesn't address all the anisotropies we see in it, all
Yes.
these temperature fluctuations. Like no other model besides the Big Bang has been able to explain that pattern. So
Yeah, the Big Bang with inflation. And yeah, I mean, Lerner has been thoroughly debunked and discredited. I mean, the people that cite him should really do some more reading on the topic, because literally there is no known physics that can create the cosmic microwave background other than the consensus view, the lambda CDM model. Lerner has gotten the closest to trying to propose something, but I mean, it's just this plasma cosmology stuff that people latch onto. It just falls apart under scrutiny. I mean, the lack of blurring that we observe is really damning to the theory as far as I'm concerned. Like the fact that we don't observe any blurring kind of rules out the plasma cosmology or the tired light views. So
on
yeah,
the
Andrew,
subject
you're pretty familiar with the different people making a lot of claims about the James Webb. So I just wanted to kick it to you. Do you think that there's any general misinformation out there that we have not addressed in this talk?
I guess one of the things I was thinking about was you've probably heard the supposedly two massive galaxies to have existed, the six found by Labbe et al. And collaborators at redshifts of, I think, around 10 or so. So that'd be roughly 500 or so million years after the Big Bang. So slightly older than the ones you were talking about, but still, if their masses and redshifts were confirmed, that would be problematic for the current LCDM model. What I think people need to keep in mind with those, however, is in contrast to the ones you were talking about earlier, where we do have spectroscopic information for those galaxies, these two massive galaxies, those we just have images for. We don't have any spectra taken for them just yet. And so their redshifts and maybe their masses might be one possibility that I'm keen on seeing if future data turns out to verify it or not, is what's called a variable initial mass function for star population. So basically measuring how many massive stars to low mass stars, and therefore how you can determine the mass of a distant galaxy based on the light you receive from it, to kind of simplify it. If that's not exactly how we think it is for nearby galaxies, then our mass estimates for these very, very distant galaxies could be off. And it turns out one paper, and maybe others that I haven't looked at, have actually shown that if you tweak it so that the variable or the stellar initial mass function can change depending on local conditions, these galaxies aren't in conflict with the lambda CDM model. Their stellar masses go down a lot.
So this actually transitions well to kind of how I wanted to end the video, which was talking a bit about some of the really cool things that the James Webb could potentially discover within the years ahead. So really quickly to touch on what you just said, I just do want to point out that for the relatively small number of galaxies for whom the James Webb has actually got the spectra for to precisely determine the true redshift, almost all of those, whenever we've gotten spectra, have been less redshifted than was initially thought. So you had that first couple weeks where everyone was going crazy. Oh, these galaxies are impossibly far, and all the headlines that the journalists were coming up with, and people on Twitter and Eric Lerners of the world. And then they recalibrated. They recalibrated the James Webb, made it a little bit more precise. Those redshift values were less than before the recalibration. But then they got the spectra and found that they were actually a lot less on average. So it could just be that the universe was dustier than we thought. I mean, dust has the effect of shifting things towards the infrared. So, and also Tanya was saying that without inflation, the cosmic microwave background wouldn't be the same. Inflation is not observable and has no known causes, except, Tanya, you might want to look at the baryonic acoustic oscillations that have been observed in the cosmic microwave background, that they actually had adiabatic heat transfers observable, which was a direct prediction of inflation. So again, you're saying inflation is not observable, but inflation does make predictions which are observable and have been observed and validated. So again, that's how science
I would
works.
probably say the opposite is the true. Actually, we have lots of models and mechanisms that could have kickstarted inflation. The problem is testing between them and seeing which specific mechanism is the correct one. So
So lots of creationists in particular seem to misunderstand this point. They'll say stuff like evolution is not observable, the Big Bang is not observable. First of all, scientific theories make observable, falsifiable predictions. Those are what are tested. You test the predictions of your theories. You don't just test the theory directly. You test the predictions. That's how science works. So if you understand how science works, you wouldn't be making these kinds of assertions.
She also said homogeneity and isotropy were incorrect predictions. I wouldn't necessarily say that. I would say the degree of isotropy was suspicious, because it's not like the Big Bang per se predicts the degree of isotropy. It just is. It should be roughly homogeneous and isotropic.
And it is. I mean, the anisotropies observed within the cosmic microwave background are on the scale of like 1 part in 10,000 or something. It's pretty dang homogeneous. So for this final part, I just want to transition to some of the very cool things that we may discover with the James Webb, particularly talking about the most distant, the cosmological stuff, not necessarily exoplanet stuff. I mean, that is a huge aspect of what the James Webb is going to be looking at, is exoplanets. But personally, I'm really hoping that we can get a little bit more insight into the behavior of dark matter in the early universe. That seems to be kind of a key area that could help to explain some of the things that we've been observing with galaxies forming extremely quickly, having really high rates of star formation within them, being extremely bright. Our understanding of how dark matter works may just be refined by some of this early universe data in some really, really cool and exciting ways. So I'm really, a lot of these different theories about what dark matter is or how it works, the James Webb might actually be used to sort of differentiate between those theories and which ones matches most closely with our observations of the early universe, which I'm super excited about.
Like dark matter right now, the models for it are pretty much the simplest ones. So like, could it self-interact with itself? Is it a more complex kind of particle than we're thinking right now? That'd be an interesting question that the JWST could help answer.
Yeah. And then additionally, the formation of the supermassive black holes in the center of most galaxies, like that is going to end up being, so one of the key insights that the James Webb is potentially capable of giving us, because right now it's really a mystery about how, why each galaxy has a supermassive black hole at its center. And the James Webb observations might go a pretty long way at explaining at least how they were formed and what kind of physics is involved there. And again, that potentially has a lot to do with dark matter as well. So those are some of the things that I'm most looking forward to from the James Webb. I mean, it's going to revolutionize our understanding of the very earliest formation of galaxies. We could potentially be seeing the first population 3 stars observed, which again would be a huge validation of a Big Bang prediction. We're already seeing the reionization, like direct observations of reionization occurring, which is super excited. Another validated prediction of the Big Bang. And yeah, those are probably the things that I'm most excited for the James Webb, is to revolutionize our understanding of early galaxy formation and the behavior of dark matter. Anything that you'd like to add onto that, Andrew?
Yeah, I'd say probably, yeah, that stuff, because those are still open questions that we definitely need more data to help answer. Yeah, I just say off the top of my head, like I was saying earlier, with how star populations, maybe, I don't know if how these early stars formed in particular, like if there were different mechanisms going on, but maybe at least, like I was saying, whether stars in the early universe were significantly different, either on average or just locally compared to modern stars and galaxies.
Mm-hmm. Yeah, and the actual, I mean, I've been waiting on the edge of my seat for some of the spectra data. A lot of it started coming in just this year in 2023. So as we get more and more full spectrums for some of the earliest galaxies, that's going to be huge as well. And so a lot of people have been trying to make a lot of really big claims based on the very earliest first data that the James Webb has been putting out. And I
Right.
hope that during this stream that we have shown how fallacious and rather absurd a lot of their claims have been. So with that note, I think I'll end it here. No creationists showed up to try to talk about the James Webb. Maybe they felt a little bit out of their depth, or Sea Science was having technical issues. Who's to say? But yeah, I think I'll leave it here. If you are a creationist out there and you do take issue with the James Webb results, and you think that they somehow prove Genesis or disprove the Big Bang, go ahead, email me criticalbasedinquiries@gmail.com. Let's set up a discussion about it. I'd be definitely interested in having a discussion on the James Webb data. And look out for a new debate tomorrow. Someone actually emailed me, said that they saw Kent Hovind debate with me and wanted to have a debate on evolution and specifically the law of monophyly. So that should be a good one. A little bit of a surprise guest, a mystery bag. We'll see what we get. But that's going to be tomorrow at 7 p.m. Central. So look out for that as well. And I will be doing another based theory on what thoughts are made of next week. And finally, I've been trying to, some of you have brought to my attention that James Tour actually shouted me out in particular on a new stream that he did just a couple days ago. I've been trying to download that stream so that I can make a video response to it. He basically called me a clout chaser and said that he will not debate me because he doesn't want to platform me and give me more views. So, you know, he didn't actually address anything substantial, scientifically substantive, but we should still have a lot of fun with debunking him yet again on this one. And since it's my most viewed video, the debunk of James Tour, I'll have plenty to debunk of some of the comments section for that one. So look forward to those videos on the horizon. Again, I'm happy to be back doing streams, debates, and videos again. So thanks for everyone that patiently waited the last month or so. And yeah, look forward to more content from me now. Thanks, Andrew, for showing up to the stream. I always appreciate your inputs. And
Yeah, thanks for
personally,
having me on.
I love talking about this stuff.
Yeah, me too.
Yeah. All right, everyone. Well, have a great night and look out for those upcoming videos. Talk to you later.